Everyone, this is Ashwini from Sri Venkateshwara College of Engineering, affiliated to VTU. So, today's topic is nothing but joint probability distributions for two discrete random variables, its expectations, its covariance, and its correlations. So, this is the joint probability of when x is equal to 3 and y is equal to 2. So, let's move on to what is joint probability. Joint probability distributions. So we'll see what is the concepts of joint probability distributions. So biological systems are usually described not only in single random variable, but in many genuine variables, random variables. So example, the expression state of human cell is 20,000 random variables xi for each of its genuine. We will start with its just two random variables x and y that generalize when it's necessary. So when a joint probability is given in two random variables that are defined on the same probability space, the joint probability distributions is corresponding probability distributions. On all possible pairs of outputs, the joint distributions can just as well as to be considered for any given number of random variables. The distributions can encode the marginal distributions, that is, the distributions of these individual variables, and the conditional probability distributions, which deals with how the outputs of an individual variable are distributed when given in the information on output of other random variables. So this is the concept of joint probabilities, and still in the formal mathematical setup of measure theory, the joint distribution is given as push forward measure by a map obtained by pairing together a given random variables of sample spaces that probability is measured. In case of real valued random variables, the joint distributions as a particular multivariate distributions may be expressed by the multivariate. Cumulative distribution functions are by multivariate probability density functions together with an multivariate probability mass functions. In this, the special case in continuous random variables, it is sufficient to consider the probability density functions, and in case of discrete random variables, it is sufficient to consider the probability mass functions. So each of the four inner cells shows the probability of how particular combinations of results from two draws, and these probabilities of the joint distributions in any one of the cell probability of particular common occurring in the products for this probability, and it is specialized within the probability of specified result for B. So next we'll see what is the expectations. In this section, we study further properties of expectations of random variables. We move on from expectations of single random variables to consider the expectations of functions of collection of random variables x1, x2, and x0, xn1, 2. We pay particular attention to the expectation for the functions of two variables, that is x and y. So we define a covariance as a measure of how random variables x and y vary together, and correlation which provides a measure of linear dependence between the two variables x and y. So this is the example x1, xn. So next we'll see what is covariance. The covariance of two random variables x and y is defined as curve. Covariance can be called as curve. Curve of x comma covariance of x comma y is equal to e of x minus e of x. So y e minus e of y, close the bracket. So covariance has following important properties. Covariance is equal to the expected value of the product minus the product of expected values. Covariance is equal to the expected values of the product minus product of expected values. The covariance is two equal random variables, which is equal to the variance of random variables. The covariance of the scalar multiple of random variable is equal to the scalar of this covariance, and additionally covariance is invariant under the addition of constant which is either argumented. Covariance of Ax plus b, Cy plus d, that is equal to AC of covariance of x, y. First, we'll see what is correlations. Invariance of x is greater than 0, variance of 0 is greater than 0, and variance of y of the greater than 0, variance of x, then correlation of x and y is defined as pi of x, y is equal to covariance of x, y, and root of variance x of variance of y. So correlation has the following important properties. So these are the properties in which -1 is lesser than equal to p of x, y, and it is less than equal to 1 minus of x, p of x, y. If x, y and are independent, then p of x, y is equal to 0. Note that again the converse is not true. So correlation is invariant under a scalar multiple of random variables which up to change the sign additionally correlations, and invariant under the additions of constant either or. Correlation is invariant under the scalar multiple of random variables up to the change of sign. Additionally, covariance is invariant under the addition of constant in either argument. So, for example, correlation between the height and weight individuals will not be affected by the choice of units of measurements of heights, weight, but the covariance will change depending upon the choice of units. So this is all for the video. Thank you everyone for watching my video. Please do share it to your friends and families.